Bismillahirrahmanirrahim. Hello everyone, I hope you are all doing well. I welcome you to the first area of number theory, which is elementary number theory. My name is Azmat Ali. In the last lecture, I discussed up to question number 8. In today's lecture, I will explain the solutions of question number 9 through 14. And inshallah, we will complete problem set 1.1 today. So, let us begin with question number 9. In question number 9, uh, we have to establish the Bernoulli inequality that can be stated as here 1 plus a is greater than 0, then we need to show that 1 plus a whole power n is greater than or equal to 1 plus n a for all n greater than or equal to 1. To prove the inequality, we use the mathematical induction. Let Pn be the given statement, then we can write Pn such that 1 plus a whole power n is greater than or equal to 1 plus na for all n greater than or equal to 1. So by using the base step, that is, we check the inequality for n is equal to 1. When we put n is equal to 1 here on both sides, we have 1 plus a whole power n, and in the right side we have 1 plus 1a. 1 plus a whole power n is 1 plus a, and the right side is also equal to 1 plus a. So this is true because 1 plus a is equal to 1 plus a. So the statement is true for n is equal to 1. Next we move toward the second step of mathematical induction. Suppose the statement is true for n is equal to k, that is pk is true, that is 1 plus a whole power k is bigger than or equal to 1 plus ka for all k greater than or equal to 1. In the third step, that is inductive step, we prove that the statement is true for n is equal to k plus 1. When it is true for n is equal to k, we will show that the statement for n is equal to k plus 1 means we will show 1 plus a whole power k plus 1 is greater than or equal to 1 plus k plus 1. So to prove the inductive step, I will take left hand side of this inequality. This can be split as 1 plus a into 1 plus a whole power k by using 1. In 1 plus a whole power k is greater than or equal to 1 plus k times a. So by replacing this factor 1 plus a whole power k with 1 plus ka, so this becomes 1 plus a into 1 plus ka. By multiplying both factors, we have 1 plus ka plus a plus ka square. Taking common a from these two terms, we have 1 plus k plus 1 into a plus k times a square. As it is given that a plus 1 is greater than 0, it means a is greater than minus 1. If a is greater than minus 1, then clearly a square is positive. And k is a natural number, so k times a square is also positive. So this term k into a square is positive. So the sum of these three terms clearly greater than 1 plus k plus 1 into a. In other words, if we left this term k into a square, then the remaining the sum of these three terms will be greater than or equal to these two terms. And in case if a is equal to 0, because here a is greater than minus 1, so it is possible that a is 0. In case a is equal to 0, then this term reduced to this becomes 0, this is also 0, this is equal to just 1. So equality hold when a is equal to 0. So this gives us 1 plus a whole power k plus 1 is greater than or equal to 1 plus k plus 1a. So this shows that the statement is true for n is equal to k plus 1 whenever statement is true for n is equal to k. Hence, by mathematical induction, statement is true for n for all n greater than or equal to 1. Next, this is question number 10. I am just sharing the solution of this question. I have written the solution in very simple and easy way, and I hope you will find the solution very easy and straightforward. In question number 10, the statement is for all n greater than or equal to 1, prove the following mathematical induction. We need to show this sum is less than or equal to 2 minus 1 by n. I am just sharing this solution. You can see here. This is very simple and easy. Similarly, question number 10b, this is a very easy and straightforward question. So okay, next we discuss question number 11 here. We need to show that the expression 2n factorial over 2 raised to power n into n factorial is always an integer for all n greater than or equal to 0. Suppose that the given statement is denoted by Pn, that is this. For the base step, we start from n is equal to 0 because in the inequality, our integer is greater than or equal to 0 here. So we check the base step for n is equal to 0. When you put n is equal to 0 in the given expression, this becomes 2 into 0 factorial into 2 raised to power 0 into 0 factorial. By just putting here n is equal to 0, 2 into 0, 0, 0 factorial is 1 and 2 raised to power 0 is 1. This becomes 1 over 1, that is equal to 1, which is clearly an integer. Inductive step. Suppose the statement is true for n is equal to k. That is just for by replacing n is equal to k in the given expression, we have 2 into k factorial over 2 raised to power k into k factorial. We suppose this fraction is equal to some integer and say this integer is m. Inductive step. We show that the statement is true for n is equal to k plus 1 whenever statement is true for n is equal to k. In other words, we will show this number 2 into k plus 1 whole factorial over 2 raised to power k plus 1 into k plus 1 factorial. This is an integer. So consider we solve this number 2 into k plus 1 factorial over 2 raised to power k. If we break this break the factorial of this number, first we multiply this number 2 inside the bracket, we have 2k plus 2 factorial. So if we break this number, break this factorial, 2k plus 2, 2k plus 1 up to 2k factorial, and we can split this power 2 into 2 raised to power k, and this can be separated as k plus 1 into k factorial. By taking 2 common from this bracket and by cancelling out that 2 with this 2, here we have k plus 1 that can be cancelled with this number. So the remaining fraction is 2k plus 1 into 2k factorial over 2 raised to power k into k factorial. By using 1, this is equal to integer m. As for all k greater than or equal to 0, this number is always odd, always an odd integer, and m is already we have assumed this is an odd integer. The product of two integer is again an integer, so this shows pk plus 1 is an integer, hence pk plus 1 is true whenever pk is true. Hence the statement is true for all n greater than or equal to 0. Question number 12. This is also an interesting question. This is here we have a piecewise function uh, when we apply t on n, it maps n into uh, two parts. When n is odd, this gives 3n plus 1 over 2, and for n is equal to even, we have n by 2. The it says that the 3n plus 1 conjecture is the claim that starting from any integer n greater than 1, the sequence of iterates tn, t of tn, t of t of tn up to so on reach the integer 1 and subsequently runs through the value 1 and 2. This has been verified for all n less than or equal to 10 raised to power 6. Confirm this conjecture in the case when n is equal to 21 and n is equal to 23. So we start for n is equal to 21. As n is equal to 21 is an odd integer, so we substitute n is equal to 21 in this part. This becomes 3 into 21 plus 1. This becomes 63 plus 1 by 2, that is 64 over 2 gives us 32. Now again we apply mapping t on both sides. This becomes t of 21 equal to t of 32, as 32 is again an even integer. This is an even integer now, so we use the mapping n by 2. So this gives us 32 by 2, that is 16. 16 as an even integer, so when we apply t again, we have t of 16, that is equal to 16 by 2, which is equal to 8. 8 is again an even integer, so applying t fourth time, we have t of 8 is equal to 8 by 2, which is equal to 4. 4 is again an even integer, so when we apply t fifth time, so for our convenience I am writing here t5, that shows t of t of t of t of t 21. So this becomes t4 t of 4 is equal to 4 by 2, which is equal to 2, and lastly when we apply again t, this becomes 2 by 2, which is equal to 1. Similarly, we can verify that t11 23 is equal to 1. Lastly, I have noted some observation from this conjecture. Why does output of 3n plus 1 conjecture is always 1? Actually, once when output of 3n plus 1 over 2 is an even, then tn is equal to n by 2 maps every input to an even integer, and repeatedly when we use tn is equal to n by 2, it ends at 1. Question number 13. Suppose that the number an are defined by inductively by, these are the first three terms of a sequence, a1 is equal to 1, a2 is equal to 2, a3 is equal to 3. The nth term is defined as the recursive relation. It is a sum of last three terms, last three consecutive terms, an minus 1, an minus 2, an minus 3, for all n greater than equal to 4. Use the second principle of finite induction, show that the nth term an is always less than 2 raised to power n for every positive integer n. Suppose the statement is denoted by p of n, that is p of n is equal to a n less than 2n, 2 raised to power n. Clearly, when n is equal to 1, this becomes a1 is equal to 1, which is less than 2. When we put n is equal to 2 here, this becomes a2 second term, which is equal to 2. It is given that second term is 2. And from the right side, this becomes 2 raised to power 2, that is, this shows 2 is less than 4. And similarly, the third term, which is 3, which is less than 2 raised to power 3, by putting n is equal to 3 here. So this statement is true for first three natural numbers, and for n is equal to 4, we will calculate this from this formula. When you put n is equal to 4 here, this becomes a3, a2, a1, which is equal to 1. A1 is 1 here, a2 is 2, a3 is 3 here, which is equal to 3 plus 2 plus 1, that is 6. 6 is less than 2 raised to power 4. So statement is true for the basic step, base step n is equal to 4. Suppose the statement is true for all k greater than or equal to 4, and assume, let for all k greater than or equal to 4, and assume that ak is less than 2 raised to power k for all k 4 for equal to 4, 5 up to so on k. Then we show that ak plus 1 is also true as nth term is a sum of the last three consecutive terms. So ak plus 1 is equal to kth term, k minus 1th term, k minus 2th term. As we are using the second principle of finite induction, so ak is less than 2 raised to power k, ak minus 1 is less than 2 raised to power k minus 1, and ak minus 2 is less than 2 raised to power k minus 2. Further, as ak minus 2 is less than ak minus 1, that is the k minus 2 term is less than k minus 1 term. So 2 raised to power k minus 2 is less than 2 raised to power k minus 1. So if we replace this number by 2 raised to power k minus 1, so this sum is less than these three, sum of these three terms. So combining these two terms, this becomes 2 into 2 raised to power k minus 1. This gives us 2 raised to power k. Again adding these two terms, this gives us 2 raised to power k plus 1. This shows that ak plus 1 is less than 2 raised to power k plus 1. That is our target. Hence pk plus 1 is true whenever pk is true. pk minus 1, pk minus 2 up to some p4, p of 4 are true. Hence by second principle of mathematical induction, the given statement is true for all. And last question. In this question, if the number a and are defined by the first term is 11, second term is 21, and the nth term is given by this relation an is 3 times a n minus 1 minus 2 n minus 1 for all n greater than equal to 3. We have to prove that this nth term is equal to this specific number 5 into 2 raised to power n plus 1. We will assume that the given statement is Pn such that our an is equal to this formula and is equal to this specific number. So to prove this specific number, we will use this formula. Here a first term is 11, second term is 21, for n is equal to 3. We check the statement for n is equal to 3. So if we put n is equal to 3 here in this formula, we have 3 into a2 minus 2 into a1 by putting just here n is equal to 3 here. This gives us the third term, which is equal to, if we put here n is equal to 3, this becomes a3, and if we put n is equal to 3 in this side, this becomes 5 into 2 raised to power 3 plus 1. So the third term from both sides, from the left side, this gives us 41 after calculation, and the same result we can find from the right side, which is also 41. So the statement is true for n is equal to 3. We suppose that the statement is true for n is equal to k minus 1 up to so on for 3. That is, again I am using the second principle of finite induction here. A statement is true for all n less than or equal to k. This shows that our ak is equal to 5 into 2 raised to power k plus 1, as well as ak is equal to 3 into a raised to power k minus 1 minus 2 into a raised to a k minus 2. We show that the statement is true for n is equal to k plus 1 here. So what we need to show here, the k plus 1th term should be equal to 5 into 2 raised to power k plus 1 when ak plus 1 is given by this formula 3 into ak minus 2 into ak minus 1. So consider ak plus 1 is equal to 3 into k, ak minus 2 into ak minus 1. Using here, by putting the value of ak, which is equal to 5 into 2k plus 1. How can we find this kth term? By just replacing here n is equal to k in this formula. We will show that the result is true for n is equal to k plus 1 on the base the result is true for n is equal to k and k minus 1. So for n is equal to k, ak is the kth term is this, and the k minus 1 term is can be written as this. So by substituting the values of kth term and k minus 1 term here, we have 3 into 5 into 2 raised to power k plus 1 minus 2 into 5 into 2 raised to power k minus 1 plus 1. Multiply 3 inside the bracket, and similarly here 2. We have 15 into 2 raised to power k plus 3 minus 5 into 2 raised to power k. Multiply this 2 with this number 2 raised to power k minus 1. This gives us 2 raised to power k. And 2 into 1, this gives us minus 2. By subtracting these two numbers, 15 into 2 raised to power k and 5 into 2 raised to power k, this gives us 10 into 2 raised to power k, and plus 3 minus 2, this gives us plus 1. This number can be written as 5 into 2 raised to power k plus 1, because you can write 10 is equal to 5 into 2. So this becomes 5 into 2 into 2 raised to power k. This gives us 5 into 2 raised to power k plus 1, which is required to show. Hence the statement is true for n is equal to k plus 1 whenever the statement for n is equal to k minus 1 up to some statement for n is equal to 3 are true. Hence the statement is true for all positive integers. So in today's lecture, Alhamdulillah, we have completed problem 1.1. Inshallah, in the next lecture we will discuss about binomial theorem. So if you find these my videos are helpful for you, kindly like, share and subscribe my channel. Okay, take care. Allah Hafiz.